A warm welcome to everybody. Today we have Professor Elina Shishkina, who is a full professor at Faculty of Mathematics, Applied Mathematics, Informatics, and Mechanics at Voronezh State University in Voronezh, Russia. She graduated from the Department of Mathematics at Voronezh State University in 2004. Elina Shishkina completed her PhD thesis in 2006 and her doctoral thesis in 2019. Her primary research interests lie in mathematical analysis, differential equations, with a particular emphasis on fractional calculus and its diverse application. We are very happy to have you here. You may please begin your talk.
Thank you very much, Pavan. Thank you all for coming, and it is really great pleasure for me to have a talk at this seminar. This seminar has a very great history, and it is really big honor to take part in this seminar for me. So first, the small information. This is my Voronezh State University of Russia. This is my first place of work. And this is the Belgrade State University of Russia, my second place of work. And from this year, I have the third place of work. It is Chechen State University of Russia in Grozny. Now, about my subject. Often researchers consider fractional powers of the operator just d operator, which is the first derivative. And historically, people were interested in the fractional power of this operator. It means that they considered fractional derivatives and fractional integrals. But now this subject is very popular. In Russia, it became popular because of the famous book of Samko Kilbas-Marichev about fractional calculus. But before it, of course, there were a lot of interest in this subject also. And my subject is the study of fractional powers, not of the d operator, but the Bessel operator. The Bessel operator is presented in this slide. It is the second derivative plus gamma divided by t and multiplied by the first derivative. This operator is the singular differential operator, and as you can see, it is for natural gamma, it is a radial part of the Laplace operator. But also this operator appears in many applications when gamma is not natural. For example, 1/3 gamma when is equal to 1/3. It is very often to see in different physical books about everything. So in our Voronezh State University was Ivan Kipriyanov, who was the chief of my department, and he initiated this subject concerning Bessel operator, and he considered a lot of different problems, but the main part of his work was singular elliptic problems. As for me, I continued his subject of, in the first steps of my career, and I considered different potentials, so-called RIS potentials. It is fractional power of a Laplace-Bessel operator, where we took instead of the second derivative, Bessel operator. And when I started to consider this subject, I was interested in general fractional calculus, and I was thinking about what will be if we take the fractional power of the Bessel operator. And I started to ask, and my co-author, Professor Sitnik, told me about the paper of Ida Springheiser-Cooper, and this paper was published in 1979. And in this paper, first appeared fractional powers of the Bessel operator. Next, in the book and in different papers of Professor McBride, we can find so-called hyper-Bessel operators and fractional powers of hyper-Bessel operators. These operators much more difficult than Bessel operator, because it is something like iterated Bessel operator, and McBride obtained a lot of results about hyper-Bessel operator and its fractional powers. Next, Virginia Kiriakova, Ivan Dimovsky considered their very generalized fractional calculus and applications, as well as Abreshkov transforms. And they also considered hyper-Bessel operator, its fractional powers, and different aspects of this operator. But from the point of view of this general case, we can see here Adam McBride. His advisor was very well known Arthur Erdely, and we can see Ida Springheiser-Cooper. Her advisor was Tom Krovinder, but actually I found only one paper about Bessel operator, its fractional powers of Springheiser-Cooper. Probably she decided not to write about this subject anymore, I don't know. Here we can see famous Bulgarian mathematicians, Ivan Dimovsky, Ivan Dimovsky told me that he did not have any supervisor, just he was by his own, and all his famous results were his own results. And Virginia Kiriakova, her advisor was Ivan Dimovsky. Now she's one of the most famous people in the fractional calculus, and she is a chief editor of the journal about fractional calculus, and she also did a lot of for fractional calculus, and she works very hard and now. And in her papers and in papers of Ivan Dimovsky, Ida Springheiser-Cooper, and Adam McBride, we could find a lot of information about Bessel operator and its fractional powers. But how we can obtain these fractional powers? It was written in the pioneering paper of Springheiser-Cooper. Actually, she considered this equation second, where k initially was a natural number. So it is just iterated operator. And to this equation, she added some conditions. And she obtained the solution of the problem 2-3, and this solution was written as this integral operator. We can consider this operator as integral operator, and if we put here instead of k any positive real or even complex number, we will obtain the fractional integral, which will be fractional integral, fractional power, negative power of Bessel operator. So it was first step. What we do not like here, this this unit in the upper limit of integration. Actually, as you know, in real life and in fractional calculus, it is better and it is more convenient to consider integrals from 0 to x or from x to infinity. It is more natural. When we obtain all formulas which we have in usual calculus with natural powers. So what we have here in formula 4, of course, everybody knows this hypergeometric Gauss function and Pavan symbol, and we can now introduce left-sided fractional Bessel integral on a semi-axis by this formula 7. What change? The limits of integration, and here, of course, we should put x and y in the right order. We do not want to have some complex branch or something like that. So from x square, we should write x square minus y square here. So we can introduce this fractional power. Of course, we need fractional derivatives, and we can introduce a lot of them because, as you know, and everybody knows, that we can introduce as much fractional derivatives as we want. And now we have a lot of different papers about fractional operators in any kinds. But here we would like to consider only two. One, it is just something like Riemann-Liouville type, when we take integral and then we take iterated Bessel operator. And next, the 9, it is Caputo type. First we take Bessel operator iterated and then fractional integral. Of course, when alpha is natural number, we should obtain iterated Bessel operator. In McBride book and in McBride papers, we can find special spaces. What we would like to have in order to solve differential equations with the fractional powers of Bessel operator. We would like to have good behavior at x and at infinity, because when we deal with the Bessel operator, it is a singular operator and we have a singular point at 0. And in this case, we should have this condition x in power k and multiplied by derivative of phi of order k should tends to 0 when x tends to 0. And we can consider 3 classes of functions here in order to obtain this theorem. This theorem was obtained first by McBride, but for the hyper-Bessel operator. And here I just rewrite it for my case, for the fractional powers of Bessel operator. So we can see that this fractional powers is a continuous linear mapping from f pi mu and into f pi mu minus 2 alpha. And also we can see that the inverse operator exists for also these spaces, which was presented by McBride. What next? Next, we can see how to write just left-sided fractional Bessel derivative for the case when alpha is from 0 to 1. It is important case because here we do not have iterated operators, but only one Bessel operator in the integral, and this is Caputo type fractional Bessel operator. What next? We would like to check when gamma is equal to 0, instead of Bessel operator, we will obtain just the second derivative. And if we put gamma is equal to 0 in our formulas, we will obtain just Riemann-Liouville integral of order 2 alpha and Riemann-Liouville fractional derivative. So this definition is correct from this point of view. What next? Also McBride obtained the factorization formula for the hyperbessel operator, and here we can write this formula for our fractional power. Here factorization using two RD-Cabert operators, and it is very important because when we would like to calculate something, it is much more easier to calculate iterated RD-Cabert. For example, when we solve something, we just calculate the first integral and then we calculate the next integral, and it is much more easier. The next thing, we would like to start consider, we would like to start to solve differential equations. And what we need if you would like to solve differential equations, we would like to have integral transforms. The first one is Mellin transform, very important, but not in each case convenient, but we would like to start from something. Mellin transform is very well known. The direct Mellin transform is very easy. It is just integral from 0 to infinity x in power s minus 1 multiplied by f dx. But the inverse, very complicated thing. It is complex integral, and it is for ordinary people. It is really hard to calculate it. Inverse Mellin transform. And what we can do with our fractional powers? We can calculate fractional Mellin transform of our fractional power, and we will obtain just these gamma functions and the shift. And this formula practically the same that in the case when we have Riemann-Liouville integral and Riemann-Liouville derivative. So with when we have derivative, we should put minus before 2 alpha. It is not convenient for us to use Mellin transform for our goals because my primary interest is partial differential equations. And I would like to solve them using nice instruments without shift. And I wanted to have something like Fourier transform and Laplace transform. And I was looking for a long time for this Meijer integral transform, but all after that, I was founded, and Professor Kiryakova wrote me that she found it many years ago. In general case, it was Abreshkov transform. But what should we do? We just should say yes, I agree. And I checked it the simplest case when gamma is equal to 0 and gamma is equal to 2, it just Laplace transform multiplied by some power of psi. And also inverse transform for the Meijer integral transform, which has this modified Meijer function of the second kind as a kernel. The inverse transform is also very complicated. It's also complex integral. And also it has another kernel. It is kernel with the modified Bessel function of the first kind. And I had a problem when I worked with this Meijer transform because it was very hard for me to find the inversion. And as you know, we have quite well known tables of Laplace transform. Also, we have Brachkov, Prudnikov, and Marichev books where we can find a lot of different integrals, but not all integrals we can find, and sometimes we should calculate it in order to obtain inverse integral transform. And what we can do in this situation? It is well known that with the Bessel operator, transmutation Poisson operator is it is this Poisson transmutation operator transmute the second derivative into Bessel operator. So we have such operator, and we know that this operator is just a Rudey-Colbert operator from the fractional powers of U. And we know inverse operator for this. It is formula 15. So if we consider modified Meijer integral transform, we can use this integral representation of Bessel function, and we can consider our Meijer integral transform in this factorization form. So instead of calculating the complicated inverse Meijer transform, we can now calculate only inverse Laplace transform. And for inverse Laplace transforms, we have big tables, and it is more or less easier. Actually, these results can be found also in general form in Kiryakova books and in Kiryakova papers. Here, these papers about this hyperbessel operator, and what about operational method in fractional calculus. It was presented by Luchko in general case, And he also obtained a lot of interesting results how to use operational methods, which is also method using Laplace transform and Meijer transform. This all can be found in these papers. So what for our case? The modified integral transform acts to fractional power of Bessel operator by the formula 17, and it is just very easy because we can see that power will be just multiplier here. And next, the image of the function. Very simple formula, very close, similar to the same formula for the Laplace transform. Also, for the iterated Bessel operator, we have formula 18, which is also has the same form as for regular iterated derivative. But here we have some extra conditions, as we can see in some for some values of gamma, for gamma which is equal to 1. Next, we need such space as C if M, which is just a space of Cm functions which have m times continuous derivatives, but all odd derivatives at 0 are equal to 0. And for such functions, we will obtain our results about fractional differential equations. Here we can see the general formula for the Meijer transform of the fractional power of Bessel operator, and here this power is positive, and this is the just Bessel fractional derivative. And also formula has the same structure as the formula for the Laplace transform and Caputo derivative. So it's time to solve something. This also probably well-known results, but I would like to present it because it is really understandable and clear. We start from the fractional ordinary differential equations of the form 20. We should add conditions 21. These conditions are necessary because Bessel operator is singular. And also we should add conditions 22, so we will have initial value problem for equation 20, and we would like to solve it. Of course, we can use here our Meijer transform and inverse Meijer transform, and we will obtain the next theorem, that fundamental system of solution to the equation 20 is built by the following n functions. And this is Fox-Wright functions, which are solution of our equation 20. So we obtain these Fox-Wright functions, a lot of them, and we also can construct series with these functions. And this series will be unique solution to the initial value problem 2022. This series, power series with the Fox Wright functions. Fox-Wright function is the function which is presented by this power series, and since alpha and beta here is not necessary natural, and in the fractional calculus it is always not natural, it is sometimes real, sometimes even complex, so it is not easy to deal with this function. Even asymptotic behavior, it is very complicated thing. This function was, of course, studied by Fox and Wright and other mathematicians, and now we hope we will obtain a lot of information about this function and more general functions such as Fox function H in Wolfram Mathematica with the help of Professor Marichev. What next? Each time when I obtained something very complicated, I would like to check this in the simplest case. The first simplest case here is the case when alpha is equal to 1. When alpha is equal to 1, we will obtain just very simple problem 23, 24. So, it is very well known that solution of this problem is just normalized Bessel function. It is just eigenfunction of this equation 23. But I wanted to check, and I just took this Fox-Wright function, put all constants instead of alpha, I put 1, and I obtain this series. And of course, using some formulas as Legendre duplication formula, I obtained this series, and this series fortunately is the normalized Bessel function. So it means that all previous results were correct, and this function is very well known, and we can see this relation, and it means that this normalized Bessel function is eigenfunction of Bessel operator, and also why it is normalized, because when we put argument here is equal to 0, we just have that this Bessel function is equal to 1. Oh, sorry. So, from this point of view, we can consider Fox-Wright function, which we obtained earlier, as a generalization of this normalized Bessel function. The next check. When gamma is equal to 0, we will obtain just regular equation with the Caputo derivative. Also, very simple case. And in this case, we know that the solution of this fractional differential equation with the Caputo derivative is just Mehta-Leffler function. It's called generalized Mehta-Leffler function because it has two parameters. Also, I did the same checking. I put gamma is equal to 0, and I obtained this Mehta-Leffler function as well. So it means that Fox-Wright function 2 psi 2 can be considered as a generalization of the Mehta-Leffler function as well. What is the next? Next, we can just add some some arguments, some constant a, and also obtain these results. But we would like to solve more complicated problems. And it is very well known that if you would like to solve problems connected with ODE, we should have convolution product. But what is the convolution product for the Meijer transform? It is the formula 25. And we can see here 3 integrals. And unfortunately, I checked it. It is just this operator. It is just a convolution for the Meijer transform. It is complicated, but what we can do? We should check this equation 26 when we act to this convolution. By our Meijer transform, we should obtain multiplication. Here we have some power function and gamma function, but it is okay. We can work with it. Of course, we can here improve our convolution product and put it here, but it is okay for me. It is enough to solve ordinary differential equations. Next, I would like to consider this function only, also Fox-Wright function. And I obtained, this result was obtained actually with my PhD student. Zarakhokov Azamat from Vladikavkaz. And we obtained this solution of the problem with the right part here, not homogeneous equation, not eigenfunctions, but also here we can see function g, and we will obtain this convolution with our previous kernel, and also this Fox-Wright function. What next? Next problem was the following. Zarakhokov solved so-called mixed equations, and his PhD thesis was about mixed equation, different kinds. What means mixed equation? It means that we can have one domain, and in one part of the domain, when, for example, y is greater than 0, we have one type of equation, for example, hyperbolic. And when y is less than 0, we have another type of equation, for example, elliptic or parabolic or something like that. And what is the problem? The problem is to construct the unique solution which is continuous in all domains. It is not very new problem. It was problem which was started probably by Trikami, next Bidzadze, and others solved such problems, and this subject is very popular now also. Professor Kilbas solved these problems, mixed problems, with the fractional derivatives. And my PhD student decided to solve these problems with the fractional Bessel operator. So we should now move to the next problem, which is the simplest one for the PDE equation. We would like to solve problem 29. It is mixed in the regular sense, because we have initial conditions and also we have boundary conditions. And this function 28 is a solution for the problem 29. It was obtained using the previous results about ordinary differential equations with the fractional powers of Bessel operator. So, what we need here? We need a lot of things. Tau is 4 times continuously differentiable on the segment 0L and finite. And in this case, this series 28 uniformly converges. And all necessary functions are continuous, because when we deal with mixed problems, it is very important to obtain continuous solution. In this line, y is equal to 0. We should glue our solutions to different solutions of 2 different equations. For example, Zarahovo solved this mixed problem 30. In one, it is not very complicated from the general theory, but it is complicated because it has fractional power of the Bessel operator. When y is greater than 0, we have this fractional power, and so-called probably hyperbolic, probably parabolic, because when alpha is from 1 to 2, it is parabolic, and when alpha is greater to, from 0 to 1/2, yes. When alpha is from 0 to 1/2, it is parabolic, and when alpha is greater than 1/2, it is hyperbolic, because Bessel operator is the operator of the second power, the second order operator. So he solved this problem 30 with the conditions 31, and also for the mixed type problems, we should have gluing conditions like 32, 33, and 34. And he obtained, of course, we know solutions for different values of y. When y is greater than 0, we obtained the solution is 28. And of course, we know the solution for the hyperbolic equation. It is very well known. But what is the problem in such a case? The problem is to prove that we have a unique solution, and this solution is continuous. So it was proved, and the condition for this was obtained in the form 35. So that's all results which I wanted to present you. Next, you can see some my results, some books and a big article, and with my colleagues from Uzbekistan and with Professor Sitnik, we published fractional calculus tutorial book for for students in Uzbekistan. Also, I would like to tell you that this year is very important for us in many different sides of our life. And for me, it is a great pleasure to tell you that this year is the jubilee year for Oleg Igorovich Marichev, who was born in September 7 in Soviet Union, and he is now American mathematician and very well-known specialist in fractional calculus and special functions, and in integral transforms, different kind of integrals. And of course, he is one of the main developer of Wolfram Mathematica. So I just even can imagine how many different results, PhD theses, doctoral theses, books, equations, and anything else can be solved only because Oleg Igorovich write how to solve integrals and integral transforms. So it is very nice to see Oleg Igorovich now, and it is really very big pleasure for me to tell you that in this year, he has his jubilee. Also, I would like to add one thing, that in previous year, Chanpin Li, who also took part in this seminar in the previous year, did a great job. He translated the big book of Samko Kilbas-Marichev about fractional integrals and derivatives to the Chinese language, and it was printed in 2024. And Oleg Igorovich and I, we wrote the big appendix for this book about computer implementation of fractional calculus in Wolfram Mathematica, which was done by Oleg Igorovich. What about my books? You can see here the one book with Professor Sitnik, and another book with Professor Sitnik, which was published in Elsevier Academy Press. And the last picture, it was very nice times when we all can meet together in different conferences and seminars and scientific events. And this conference was in Sofia, in the heart of the fractional analysis, because this conference was organized by Virginia Kyriakova, and it was very big pleasure for me to take part in this conference. I saw Ivan Dembowski, meet him, talk to him, as well as with Professor Virginia Kyriakova and many others, people from fractional world I met in this conference, and now a lot of these people are my good friends. And now it is very important that Arran and Pavan continue this tradition to meet and to collect people together. It is very nice. Thank you. And thank you for your attention. Thank you.
Thank you very much, Elina, for the talk. It was really a pleasure for us to also organize this seminar series and bring pretty much people from all backgrounds together so we can proceed in a more holistic manner. For questions, if you please raise your hands. I'll call out your name as, okay, I see one raised hand. Yes, Professor Luchko. Professor Luchko, you can unmute your mic and ask your question.
So I am very glad to see you, Elina, today. And of course, I am very glad to see Oleg today. And first of all, yeah, thank you very much for your very nice presentation and for exceptionally good results. You demonstrated in your talk that you are able to deal with very complicated objects, with functional spaces, with operators, and with investigation of special functions, and with all of this stuff. So very interesting. And in fact, I have just maybe a comment, not a question, but a comment, that as you already mentioned, the Bessel operator that you dealt with is a particular case of the so-called hyper-Bessel differential operator that was investigated by Ivan Dimovsky and Virginia Kyriakova and so on. And I guess that at least some of your results could be probably extended to the case of more general hyper-Bessel differential operator. Did you try to do this? Are you going to investigate some more general case?
Actually, I thought about it. Thank you very much for your question and for your words. I thought about it, and I was thinking about just more general case, not hyperbasic, but I wanted to take function next derivative and in power m, for example, m1, and next another function, and again derivative, and a lot of them iterated something with different functions. Not only because in hyperbasic operator we have only power function between derivatives, and I wanted to take general case when we have just any functions, but it took me to the so-called umbral calculus, and it is a complicated area for study, and now I just to try to understand and try to read about it and try to investigate it. But yes, I would like to continue, and I would like to spread on my results to the more general cases, and not only my results, and also results of my PhD student.
Yeah, and probably another direction, even more complicated, would be to investigate the so-called Erdős-Kober fractional derivative, because the hyper-Bessel differential operator is a particular case of the Erdős-Kober fractional derivative. So
Yes,
another probably important connection from your results to more general results.
Yes, from this point of view, it means that actually Erdős-Kober operator in general case, it is just a fractional power of Riemann-Stieltjes integral with the measure, which is just a function, j, for example. And this is the subject which we study with my co-author Vasily Kolokoltsov, which I know you all know him. And we studied this case when the measure is not necessarily the regular measure. It can be some kind of negative measure or just measure with different sign, not ordinary measure, but generalized measure, because Vasily Kolokoltsov studied stochastic processes, and we would like to study the case when instead of measure we can put processes. So from this point of view, we study fractional powers and fractional Erdős-Kober operators.
Yeah, thank you. Thank you, Elina.
Thank you very much for the question.
Professor Karimov, can you unmute your mic and ask your question?
Thank you. First of all,
I want to say
Professor
something.
Eushkina, for your nice talk. I have two
When I
questions.
tell the remark, Elina forgot to say that we made appendix for this Chinese translation together with her. It's big appendix. It was published also on English, not only on Chinese. About 70 pages about fractional derivatives and integrals, how we realized in Mathematica, and a lot of literature about this. Other remark from me, that this operator with function 2f1, it is in reality composition of two fractional integrals, and if you go to my work on, from 1972 in Доклады of Academy SSSR, we have operator with kernel Apple functions 3, Apple 3, which is more generic, and we can move in this direction for generalization. Thank you.
Thank you.
I'm happy to see you. I also to say that Yuri Luchko recommended me Elina about 4 years ago to work for preparing this appendix for Chinese translation. I'm happy to work with her. She is nice mathematician.
Thank you very much. Professor Karimov, can
Yes.
you repeat?
Could you please open the slide number 45? There's a formula 28. Yes. Here, in order to prove the convergence of uniform series, you need to estimate this Fox-Wright function from the above. Do you have this estimation? How we can find the proof of it, and maybe in some papers which is published?
Yes, I think it was published in the Crown's journal, yes.
Okay, so I will contact you to get this publication.
Yes, I will check. I think it was in this Crown's paper with Zarahohov. So I will contact you. Thank you.
Another question is if you're aware about the work of Professor Urinov. He introduced the fractional integral with a Bessel function in the kernel, appropriate fractional differential operator, and a fractional integral. And they considered the Cauchy type problems, and as a solution, they got the infinite series of Bessel functions, which can be also represented by some B-varied integrable type functions. Is it? It might be a particular case, or it fills some gaps of that fractional integral, Bessel integral, which contains the hypergeometric function in the kernel. If you're aware about this work.
Yes, I'm aware, but Professor Karimov, I mean, Professor Karimov from Fergana State University, we worked with him, of course, and he sent me his paper, but actually I wasn't be able to read it, and I'm going to read it, and I will
No problem. It was published recently at the end of the
Yes.
last year. Unfortunately, Professor Urinov passed away, and it was published in
Yes.
local journal. It was not so available. Okay, thank you very much.
Yes, I will contact Shahabidin Tuchiboyevich and we will discuss it. But
Thank you.
before this talk, I wasn't be able to do it. Thank you for the remark. I will check it.
Thank you.
I don't see any more raised hands. So if anybody has more questions or comments or remarks, you can please unmute your mic and ask it. Okay, I assume it's nobody has any more comments or questions. So this is a good point to close this talk. Thank you very much, Elina, for this
Thank you
nice
very
talk.
much.